This is part 3 of the lecture 13 video. So now let's talk about step 2 of our hypothesis test procedure. So step 2 always involves identifying our critical region, and we can do that by looking up our critical value in our F distribution table. So I am actually just going to teach you about how to do our hypothesis test procedure using output from SPSS. So the things I want you to make note of first is that the numerator that we're going to be using in our F ratio is going to be the between treatment variance, and so the numerator that we'll look up when we're looking up our degrees of freedom on our F distribution table, we're going to use the DF between treatment, and the denominator that we're going to look up is our DF error. That is the bottom part of our F ratio is the error variance. So I'm actually just going to show you how to find these two values in output from SPSS. So if you have SPSS output, it gives you both of these values for your numerator and your denominator degrees of freedom. So let's look at some output, and I'll show you where you can find each of these two degrees of freedom. So the first degrees of freedom, the degrees of freedom between groups, when you're looking at your output from SPSS, it's actually just going to be that first degrees of freedom that's listed. So your source, so the label that's next to the source you see here is called time. This will actually change depending on what your factor is or what your IV is. So in this example, we are comparing people's GRE scores over 3 different time points. So at the beginning of the semester, at the midpoint, and also at the end. So that is what our between subjects variable will be, is that we're looking at our between treatment variable, I should say. Our between treatment variable is time. We're looking at the changes over time. So this is going to be our between degrees of freedom, which is used as the numerator. So we're going to use that as our numerator when we're looking up our critical value for F. And then our denominator that we're going to use is going to be here where it says error in this output. It says error, and then we'll just use that sphericity assumed row. So in following that across, you'll see that your degrees of freedom for your error is going to be 58. So that is the denominator that we're going to use to look up our critical value in the F table. So you do need to make sure you have access to the F distribution or F table. That is available for you on Blackboard. So make sure to go ahead and open up that F table so you can follow along with looking up our critical value in that table. Because there are some more complicated aspects to looking this value up that I want to go through with you. So go ahead and download the F table and open it up to look at this with me. So when you're looking for your critical value for F on this F table, you'll notice that to look up your value, it has you look in various columns and also various rows. So the columns represent the degrees of freedom in your numerator. So as I just discussed, that's going to be 2 for this example. And then the rows represent the degrees of freedom in your denominator. In this example, it's 58. So you'll notice when you're looking at that F distribution, you actually have to go through a couple of pages in order to get to the value that's closest to 58. So you should find when looking for that denominator of 58, you'll see in our F distribution that it's actually not listed. So again, our numerator was 2, so here's the column that we want to look at. But when looking for our denominator in the rows, we'll see that we're looking for a value of 58, but that's actually not listed here. Instead, we have 2 values that are close to 58. So we know that the number 58 is between 55 and 60. So our critical value is going to be between one of those two. So let's look at the correct row, correct column. So again, the column is determined by your degrees of freedom between. And so you'll see that there are these various critical values that are associated with the degrees of freedom for 55 in the denominator versus 60 in the denominator. So the first thing I want to point out is that we're looking at the values that are not in bold. So the bolded versus unbolded values is determined by your alpha level. So the bolded scores are when you're using an alpha level of 0.01, which we were not in this example. Instead, we were using an alpha level of 0.05. So since we had an alpha level of 0.05, we are going to use the non-bolded values. So looking at these two non-bolded values, we see that associated with the degrees of freedom of 55 is that F critical of 3.17. And then the value that's associated with a degrees of freedom in the denominator of 60 is an F critical of 3.15. So we're always just going to take whichever out of these two values is a bigger number. So the bigger number is actually always going to be associated with the smaller degrees of freedom. So however you want to remember that is up to you, but we're going to take the bigger number, and again we're only looking at the unbolded values because we had an alpha level of 0.05. So looking at those unbolded values, we're going to take the bigger number of the two, which was 3.17. So that is going to be our F critical value that we're going to use in step 2 of our hypothesis test. So our F critical value is going to be 3.17. So let's go ahead and draw out the distribution and identify where that score is in our distribution. So remember that in the last chapter we discussed how our F distribution, it looks pretty different from what our T and our normal distributions were. So the F ratio is always going to be positive, and so the distribution of all the possible F values are always going to be this positively skewed distribution. So this is the distribution of all of our possible F ratios that we could get. Well, not quite all of them, because this table, this graph actually, this tail extends into infinity. So this is just really a portion of it. So just remember that this tail is always going to kind of continue on until forever. It becomes less and less likely to get really extreme scores out here. But anyways, we looked up our F critical value. Let's go ahead and draw it into our distribution and then shade in the critical region, which is always going to be the tail. So anything more extreme than that value of 3.17 is going to be considered a significant extreme score. So in step 3, our main goal of step 3 is to find our F ratio. Again, I told you that this example, I'm just going to use SPSS output to help you walk through the hypothesis test procedure. So I'm not going to even teach you how to calculate F by hand in this chapter. Instead, we're just going to locate it within our output from SPSS. So here is the output from SPSS. One major thing that I want to point out, if you're actually running your own analysis, make sure you're using the correct table. So the table is listed as tests of within subjects effects. There are other tables that sometimes look very similar to this, so do make sure you're looking at the correct table labeled tests of within subjects effects. But the place that you're going to find your F ratio is just going to be in this first row here. So in this first row, and it's, again, whatever your variable here is, it might change depending on what your factor was or what your IV was, might change, but it's always going to be in this first row here. We got our F statistic right there. That is the calculated value for F. So that is the F that we're interested in step 3. So as far as step 3 goes, when you have output from SPSS, you can just report that value. So the ultimate goal of step 3 was to calculate F. Hey, there it is. So you could just report that value for F in your step 3 of your hypothesis testing procedure. So always make sure that you're rounding 2 numbers after the decimal point according to APA style. So our F that we'll report here is going to be 193.45. So that's all you need to do for step 3 is just to report that value. So still the same rules are going to apply when we're making our decision as far as our hypothesis test goes. So to make our decision, we're always going to take that value we just calculated in step 3, that obtained F value, and we're going to see where it falls within that distribution that we set up in step 2. So again, here's our distribution that we established in step 2. And as I mentioned before, this distribution actually carries off into infinity, and so that tail continues on even though it wasn't in our initial drawing. And our obtained value in step 3 was 193.45, which is way, way out there, very extreme. It's definitely within the critical region because it falls into that extreme tail. So since our obtained value, the value we calculated in step 3, since that is indeed in the extreme tail of this distribution, that is always going to be associated with the decision to reject our null hypothesis. So our decision, since our calculated value falls within that extreme tail, our decision is going to be to reject the null hypothesis. So one complication with ANOVA, just like the last chapter, is that at this point, rejecting the null hypothesis, basically all we can say is that one of those means is different. But since we have 3 different means, we can't say yet which exactly of the means is different, or if they're all different from each other. We don't know that yet. So we actually have to do an additional step to be able to identify how these means are different from each other. So at this point, all we can conclude is that at least one mean is different, but we don't know exactly which ones. So far, we're going to start out our conclusion by saying something like this. So we'll say that a one-way within subjects ANOVA indicated that GRE scores were significantly different during at least one of the time points. So again, we know that one of the time points is significantly different. We have to do a little bit more work to really identify which, or if all, the time points were different. But before we do that, we'll just report it this way to start out our conclusion, and then make sure you indicate your test statistics at the end of that sentence. So we used an F test to make this decision. And so remember that this first degrees of freedom that you put here in parentheses next to your F, that's always the degrees of freedom for your numerator that you looked up in the table. So our degrees of freedom in our numerator was 2. We'll put a comma and then put the degrees of freedom in the denominator that we looked up. And we already talked about that in step 2, which our denominator degrees of freedom was 58. And we found that also within the output from SPSS. So it gives you both those values. But we identified each of those in step 2, so make sure to look back at that to find that information. And then here we just report the actual calculated value of F, which is the one that we got from our SPSS output. And since we made that decision to reject the null hypothesis, we'll next say that the probability, so the likelihood of getting this value for F was less than our alpha level of 0.05. So the probability of getting an F that extreme is really, really low. It's a small likelihood or small probability. So P is less than our alpha level. So that's always what we put if we had made that decision to reject the null hypothesis. So next, let's talk about effect size, and I talked about it in the last chapter, but effect size is measured by eta squared in ANOVA. And you'll see that when you look at the SPSS output, it actually gives you this value. So you have to ask the program to give it to you, I believe, but once you ask the program to give you that output, it reports the eta squared in that table. So you can go ahead and just add that effect size of 0.87. You can add that to the end of your conclusion. And next we'll talk about the rest of the conclusion and how we can add to this conclusion.